Now that the characteristic extension theorem is done, we need to know how to construct measures from pre-measures. So the most important pre-measure that we deal with is on the algebra generated by the God-given semi-algebra. This is called the Lebesgue Stieljets pre-measure, which is defined as on the semi-algebra lambda of a comma b to be f minus f a. F is increasing, non-decreasing, and right continuous. We referred to see a proof, but we know this is a pre-measure. Now, this is sigma finite also. Now, one thing, f of lambda f of lambda f of something of this form minus suppose a comma infinity, this has to be defined. So I define f of infinity as the limit. So this exists because it is non-decreasing, and define that to be f infinity minus f a. Analogously define it for minus infinity. Yeah. So this measure is sigma finite. Why? Because R can be written as disjoint union. Disjoint is not necessary, but still like this, where each of them has finite measure. If fx equal to x, that is our most important special case, then each individual component some measure 1. So this is a sigma finite pre-measure. So by characteristic extension theorem, this can be uniquely extended up to the Borel sigma algebra. In fact, we know it can be extended to M, that is set of all mu star measurable sets, and we will try to see if it can be uniquely extended up to the Lebesgue. So it can be uniquely extended to the sigma algebra generated by the algebra. The algebra consists of all half open closed sets, so it contains the Borel sigma algebra. So the algebra generated by it is the Borel sigma algebra, and the sigma algebra of all mu star measurable knives is called the Lebesgue sigma algebra. It is denoted by this. Some people use this also, L. And the measure restricted to the Lebesgue sigma algebra of mu star is called the Lebesgue measure, and that restricted to BR is called the Borel measure. And by characteristic extension theorem, we know that this extension of the measure from the algebra to the Borel sigma algebra is unique. So there exists only one measure, Borel measure, that extends this. So now this is the most important. This is called Lebesgue Stieljets, actually Lebesgue Stieljets measure, Borel Stieljets measure. And if fx equal to x, that is the most important special case we will study, that is called the Lebesgue measure. So why is Lebesgue measure important, we will say. But before that, let's an example of an so f of a Stieljets measure. So f defined from R to R, fx equal to 0 if x less than 0, equal to 1 if x is greater than equal to 0. This is an increasing right continuous function. So this is finite actually. So there is a unique extension up to by characteristic theorem up to this. So mu f of, let's call this mu f of a, we can see it's 0 if 0 does not belong to a. Why? If 0 does not belong to a, then a is subset of minus infinity, let's say minus infinity comma 0 union 0 comma minus infinity, comma infinity. Check that the measure of these two is 0. And mu of a fa equal to 1 if 0 belongs to A. Clearly, because mu of 0 you can check will be 1, and A minus 0 is again measure 0 by the previous statement, because 0 does not contain here, so that will be 0. So this measure is called a Dirac measure, or the point mass measure probably. And this will help us create many counter examples. That why we study with Lebesgue measure, not Lebesgue Stieljets measure, because there are properties, very important properties that Lebesgue measure satisfy but Dirac measure, but Stieljets measure don't. So properties of Lebesgue measure. First of all, we are actually not considering the Lebesgue sigma algebra. So we are only doing the with the Borel sigma algebra, and it's fine because of this proposition that if, so we will, for Lebesgue sigma algebra we will use this small m. If A belongs to Lebesgue sigma algebra, let's call this L, then there exists B belongs to the Borel sigma algebra, BR, such that B contains M and M of B equal to M of A. So we can actually get a space, get a Borel set containing A, so elements of the Borel sigma are Borel sets containing A, so that MB is equal to MA. So proof of this is simple. So mu star A, take a 1 by N, then you will get elements in the some Clopin intervals A comma B, so that these cover A, these some finite, some countable collections which cover it, and this is less than this. So summation, let's call this lambda A comma B cover this, and this is greater than equal to, by countable additivity, this is greater than equal to, okay, mu star union AK comma BK by countable additivity of the outer measure. So call this to be BK for Bn, for every n you get intersection Bn. So every Bn, so this is satisfied, mu star An plus 1 by n is greater than equal to mu star Bn. So then it follows mu star An is greater than equal to mu star intersection Bn, because it is smaller than every 1 by n. And the other side is also trivial because it contains the other thing, so by monotonicity. So this, each Bn's were in the Borel sigma algebra, so the intersection is also in the Borel sigma algebra, and An was in L. Actually we didn't need N in there. L is in any x, so we actually got any set in the sigma algebra, any set in x, the outer measure can be approximated, can be taken to be, can be obtained from that of elements in the Borel sigma algebra, can be that measure. So, and this is not specially for Lebesgue measure, this is true for any measure that is constructed from sigma finite pre-measure, not even sigma finite is required, from pre-measure which satisfies by calculated extension theory. One thing that I intend to say, and this is important, that by calculated extension theorem, the pre-measures that are obtained, measures obtained from calculated extension theorem are complete. and you can easily check, just verify the proof. From the proof it will be easily verified that they are complete. Extension theorem icon. So what I mean is that if mu star of A is 0, so suppose n is a null set in the in the sigma algebra that is generated by mu star knives, then if n is subset of A, then mu star A must be 0, right? And if mu star A is 0, mu star A is equal to mu star A intersection my monotonicity for any, so mu star of E is greater than equal to mu star of E intersection A complement, and the others, and this is greater than equal to, this is equal to actually mu star of E intersection A complement plus mu star of E intersection A, because that is 0. So this all are mu star, so A is actually mu star measurable, so the sigma algebra are complete. This was general facts. Now we come to that of Lebesgue. First of all, that we use Lebesgue measure are translations invariant. What I mean is that M of, so if everything is taken in the Borel sigma algebra from now on, so if A belongs to Borel sigma algebra, M of A plus R by translation is equal to M. Why I am taking Borel sigma algebra? Because we don't know if under translation Lebesgue sigma algebra stays as a, means it is invariant under translation, that if you translate an element in the Lebesgue sigma algebra, if it indeed stays an element in the Lebesgue sigma algebra as of now. So, and also it as a simple behavior under dilation. So if you take any real number S and S of A, that this is mod S, this is quite simple. So just check lambda of close A comma B plus R, this is A plus R comma B plus R, which is still B minus A. Similarly, lambda of S A comma B, if B S is 0, then it is 0. If S is positive, it is just S of B minus A. If S is negative, it is minus S of B minus A. So in all cases, this is mod S B minus A. So this happens for those in the semi algebra, hence for those in the algebra, right? Now we use the sigma uniqueness of the algebra. So define M prime as M prime of A as M of A plus R, MR actually, MR of A as M of A plus R. You can easily check this is a measure. And define M of S of A as, well, assume S to be non-zero. Okay, so if S is 0, this is 0, so this side will be 0. So S of 0 it is trivially different, and from that, for non-zero, define M of A by mod S. Check that, define the good sets like this. All such A belongs to the Borel sigma algebra R such that MR of A equal to MA. Clearly see that from these two, it happens for the algebra, right? It happens for the algebra. Use monotone class theorem. Yeah, monotone class theorem is necessary. So, and you have to use, so okay, what I am saying, monotone class theorem is not necessary. We have already proved it. So, good sets are not necessary actually. So these are two measures that agree on lambda, that is agree on the algebra. So by uniqueness of characteristic extension theorem, they agree on every set in the Borel sigma algebra. Exactly similarly, these agree on that, so this agrees for every set. So this is equal to Okay, this is what I write. MS. This is equal to MA. And hence, we prove that this is a beautiful property, this beautiful geometric property of Borel's measures. It's not true for Stieljets measure. Why? Take this Dirac measure that we constructed. So take, suppose what, -1, 0. Measure of this is what, 0, right? Measure of this is, so what I use notation, let's call this mu naught. Actually that is the standard mu naught of this is, since 0 is not here, is 0. Translate by half. Mu naught of this minus if we translate by half, this is minus half comma half, which is 1. So it's not translation invariant. Similarly, we can construct an example for dilation. Now comes another important property. Secondly, fourth, M of any singleton set is 0 under Borel measure. This is very easy because this is true for mu of v minus a. This is actually true for continuous. If we take the Lebesgue Stieljets, if we take the function in continuous, this is true. So mu of, just take this a minus 1 by n comma a, this thing. So this is 1 by n, finite continuity from above. The intersection is a, so this is 0. Oh, why I am using this? We have to use it. But as we saw, so every countable sets measure is 0, because it can be written as countable disjoint union of sets of singleton sets. So Q has a measure 0. But this is not true for Stieljets measure. We just saw that mu naught of singleton 0 is 1. So these are some important properties, and we are yet to do the most important properties. I'm not missing out new properties hopefully. That is, this property actually makes it to one of the most important measures, that is called a radon measure. So check one thing, M of any compact set, any compact set, M, if C is a compact set, this is finite, because any compact sets can be this is because if C is a compact set of R, C is contained in some A, and this is finite measure, this is finite. This is true for Lebesgue Stieljets measure also. But another thing which is important, I think the charge went, 1 second. I don't know what problem happened. Charge shouldn't. Yeah, it's fine. So, okay, maybe because there was no audio input. So what I was saying, yeah. So the most important property of Lebesgue measures is that it has inner regularity and outer regularity. So inner regularity and outer regularity means that it can be approximated by the topology. What I mean by that, if A belongs to BR, we don't know how it looks like, but we can say that there exists a sequence UN of open sets belongs to the Euclidean topology tau r such that un contain a and m of n un and this is called the outer regularity by open sets. And second, if A belongs to BR, this for this finiteness is needed. For this finiteness is needed. M of A is finite. There exists Kn belongs to TR. The TR actually not TR. Kn subset of R, so that Kns are compact. And Kn is contained in A, and M of Kn increases to above. So it can be approximated from above by open sets, it can be approximated from below by closed sets. And this property is known as inner regularity by compact sets. This and not these properties together make it into I am not giving the exact definition, but these properties together make it into a Redon measure, Lebesgue measure. So Lebesgue Stieljets measure are not Redon measures, right? Take the Redon measure. Take this -1, 0. This set's measure is 1. Any open set can't contain 0 here, right? Any open set here can't contain 0. Any open set of R here okay, no, this is not a correct example. I think I have to see, maybe this can be done for probably every Lebesgue Stieljets measure is a Redon measure. So let's try the proof, and from there we can see. I think this that every Lebesgue Stieljets measure is a Redon measure. So first, outer regularity will be satisfied. Why? So I am proving it for Lebesgue measure, but this analogous proof I think will hold for Lebesgue Stieljets also. So take MA. So we need to show that there exists. So take MA plus epsilon. This is greater than equal to a cover of lambda. Let's write it like this: lambda summation lambda close A n comma Bn. Now there is one problem for this, that this in case of Lebesgue measure can be written as this form: lambda n comma Bn. But it can't be written like this if the measure is not Lebesgue. So, and this is greater than equal to lambda union an comma Bn, which is a closed set, and let's call this to be Bk. Let's call this to be lambda u. So this is no longer lambda. This doesn't make sense. This is greater than equal to M. This is M of. So MA as epsilon is greater than equal to MU. You covers it. So clearly we get an, for every epsilon we get an MU, so that mod of MA minus MU is less than epsilon. That is M of U minus A is less than epsilon. So this shows the outer regularity. Question is, Can this be done even if it is not a Lebesgue measure? That's the yeah, that is for a Lebesgue Stieljets measure. Is this true? Okay, that I have to think. So if it is continuous, it can be done, but lamb that is yeah. So okay, this I have to think that if outer regularity holds for Lebesgue Stieljets measure also. Probably I don't think they hold for Lebesgue Stieljets measure. If it's continuous, it holds this proof, but not if it is not continuous. So okay, I have to take. So, and the inner regularity is not trivial. So, okay, so for inner regularity, the proof is a bit messy. So, you can check Folland for it. So, okay. Another thing that I wish to note is that measure of bounded sets measure if the measure of a set is finite, there is no implication that it is bounded. So M of A, true for Lebesgue measure also. M of A is finite, doesn't imply M of A is bounded. The converse is true. If A is bounded, M of A is finite, but the other side is not true. Why? Take these kind of sets. A minus A, what can I say? Minus 1 by 2 to the power k, around we can say around 1 we can take n plus 1 by 2 to the power k, comma n minus 1 by okay what I am doing n minus 1 by 2 to the power k. These are sets of measure. Each set is a finite measure. Take the union. This is an unbounded set for all n belongs to n. These are disjoint, most probably. Yeah, these are disjoint. Take k to be greater than 1 or something, not 1. If 1 will also do, but so this has measure probably 1 or half, but this set is unbounded. So these here we investigated some properties of EA measure. I have to check something that whether return measure, Lebesgue Stieljets measure are also return measures. Probably they are not. Now this gives us a complete overview of what kind of measures Lebesgue measures are. So it enjoys some nice properties like inner regularity. It's a return measure. So for an overview, Lebesgue measures, Borel measures are actually, it has over finite sets, over countable sets, its measure is 0, and it is invariant retransmission as a simple phenomena under dilations. It's a return measure, and all stuff of this makes things way simpler when we get nice looking formulas. So here we complete the properties of all Lebesgue measure, and from the next lecture we will start doing integration, developing the concept.